Pluto, once categorized as a distinct and proper planet in our solar system, was regarded as a unique object for many years. However, recent discussions led by famous astrophysicists Neil deGrasse Tyson and Michio Kaku have reignited the debate about Pluto's status, prompting further analysis of its role in the cosmos. These scientists have suggested that Pluto could potentially be on a collision course with Neptune, sparking a wave of questions. How could such a massive incident occur? What would the impact mean for both planets and the solar system at large? Are we witnessing a rare and unique cosmic occurrence, or is there a more nuanced and profound explanation behind this theory? Let's delve into what a possible Pluto-Neptune collision might imply. Once considered a smaller, more distant object in the solar system, Pluto still generates a lot of interest from scientists. According to key studies, experts agree that Pluto's orbit is dangerously close to Neptune's, causing a few astrophysicists, such as Tyson and Kaku, to express concern about the possibility of a catastrophic impact between the two. The primary concern right now is whether such an incident entails a real threat to Earth. How could this happen in the first place? Pluto's orbit is one of the most unusual in our solar system. It takes an extraordinary 248 years to complete one full orbit around the Sun, meaning that, since its discovery in 1930, Pluto has not yet completed a single orbit. However, its orbit isn't the only distinctive feature. It's also highly elongated compared to the more circular orbits of the larger planets. Additionally, Pluto's orbit is tilted by 17 degrees relative to the plane of the solar system, making it one of the most tilted orbits observed. This extreme tilt, combined with its elongated shape, adds complexity to Pluto's journey through space. An especially intriguing aspect of Pluto's orbit is its interaction with Neptune's. For around 2 decades during each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect in terms of planetary positioning. This raises an important query: why haven't Pluto and Neptune collided yet? The answer lies in the gravitational forces at play within the solar system. Immediately after Pluto's discovery, astronomers were puzzled by its orbit. Unlike the other planets, which follow relatively flat, aligned routes throughout the solar system, Pluto's orbit is tilted and elliptical, making it a subject of intense study. The fact that Pluto's orbit crosses Neptune's doesn't automatically result in a collision due to a gravitational interplay that stabilizes the two orbits. This balance, referred to as the three-body problem, illustrates how Pluto, Neptune, and the Sun interact through their gravitational forces. It helps in predicting future positions based on their current motions and the forces exerted upon each other. This phenomenon highlights how Pluto's, Neptune's, and the Sun's gravitational pull ensures the two objects never collide. Astrophysicists note that this stable interaction is maintained by a mechanism called libration, which ensures that when Pluto crosses Neptune's orbit, it does so at least 90 degrees away from Neptune, thus ensuring that the two bodies are never at the same location at the same time. Additionally, Pluto's orbit exhibits degree libration, meaning it oscillates or shifts around its path. This mechanism further reduces the risk of collision. Another important factor in Pluto's orbital stability is the gravitational wobble effect known as VZK wobbling, which explains how the gravitational pull from Pluto, Neptune, and the Sun influences each other, helping to maintain Pluto's orbit despite its seemingly erratic path. The three-body problem and these forces that govern celestial motions are critical to understanding how planetary orbits evolve. These interactions not only shed light on Pluto but also enhance our knowledge of the broader workings of the solar system. Numerical simulations conducted in the 1980s revealed that while the stabilizing forces maintained the stability of Pluto's orbit, slight changes in its initial conditions could cause its orbit to become more erratic over long periods. Despite such potential irregularities, Pluto's orbit has remained relatively consistent over millennia. Recent models have further highlighted how planets like Jupiter, Neptune, and Saturn aid in stabilizing Pluto's path. For example, Neptune and Pluto follow a resonant orbit. For every 2 orbits Pluto completes, Neptune completes 3. This resonance is crucial to maintaining Pluto's orbital stability. However, Neptune is not the only planet influencing Pluto's orbit. Jupiter's gravitational influence also plays a significant role. Even Saturn has been shown to help stabilize Pluto's orbit. These simulations suggest that Jupiter's gravity alone could maintain Pluto's orbit for billions of years, if not indefinitely. Therefore, the cooperation of Neptune, Jupiter, and Saturn is necessary to ensure Pluto stays on its current course. Without these stabilizing forces, our solar system would be more chaotic, with bodies like Pluto potentially colliding with others or being ejected from their orbits entirely. Studying such interactions aids us in more ways than one. It not only helps us understand Pluto's orbit but also gives us valuable insights into the larger workings of the universe. Given this knowledge, Pluto's orbit becomes even more intriguing when considering theories of a potential collision with Neptune. The study of Pluto's complex orbit demonstrates the dynamic nature of our solar system and how the forces acting on one object can impact the entire system. It also reminds us that even seemingly chaotic orbits can still achieve a state of equilibrium. The complexities of these interactions, and the principle of orbital resonance, play a key role in this balance, explaining how Pluto's position and velocity, even with an irregular path, can still maintain stability over time. Programs simulating these orbital mechanics have provided valuable insights into how Pluto's orbit interacts with those of other planets and stars, including Neptune. Small adjustments in the model's parameters can show how even slight changes in Pluto's position or speed could significantly alter its orbit. Despite stabilizing factors such as asymmetric libration and degree libration, Pluto's orbit can still be unpredictable. Small variations in Pluto's initial conditions could lead to large shifts in its long-term trajectory. Nevertheless, despite its apparent uncertainty, Pluto's orbit continues to remain remarkably stable over billions of years, indicating an underlying order to its movement in the direction of the Sun, even when it seems chaotic. This unpredictability presents a challenge for astronomers, who must account for the evolving nature of planetary orbits. Even though they are numerical, simulations are invaluable for predicting celestial behavior. They also demonstrate our limitations. These simulations are heavily reliant on the accuracy of their initial conditions, and even the smallest error can drastically change the results, making precise predictions difficult. The erratic orbit of Pluto serves as a reminder of the constantly changing nature of the universe. While astronomers have made remarkable advances in understanding space, Pluto's unpredictable path illustrates how much more remains to be discovered. The study of giant planets' gravitational effects, like those of Jupiter, Saturn, and Neptune, on Pluto. These ongoing discussions about Pluto underscore a fundamental truth in science: our understanding of the universe is constantly evolving. As new technologies emerge and data becomes more refined, even long-held beliefs can be challenged and reshaped. Pluto, once the ninth planet in the solar system, now stands as a symbol of how scientific progress can reshape our cosmic perspective. In fact, the interest surrounding Pluto has only intensified since its reclassification. NASA's New Horizons mission, which conducted a historic flyby of Pluto in 2015, provided a treasure trove of data that revealed an incredibly complex and geologically active world. With mountains of solid ice, vast plains of nitrogen, and possible signs of subsurface oceans, Pluto defied expectations, proving that even distant dwarf planets can possess dynamic and intriguing characteristics. This revelation has led many scientists to question the strict criteria that define what makes a planet. If Pluto, with its rich geological features and atmosphere, doesn't qualify, then what truly does? The debate has sparked broader conversations within the astronomical community, with some advocating for a revised planetary classification system, one that embraces complexity rather than adhering to rigid rules. Meanwhile, the concerns about Pluto's potential future interactions with Neptune, while largely hypothetical, are not without merit. They serve as important reminders of the delicate gravitational dance that governs our solar system. Even the slightest disturbance, caused by an external force such as a passing star, a rogue planet, or the influence of the yet undetected Planet 9, could disrupt the equilibrium, triggering unexpected changes in orbital paths. While such scenarios remain speculative, they emphasize the importance of continuous observation and modeling. Every new insight into Pluto's movement deepens our understanding of celestial mechanics and prepares us for the future, whether it involves planetary discoveries, orbital shifts, or even the rare possibility of interplanetary collisions. Ultimately, Pluto's story is not one of demotion, but of redefinition. It reminds us that in science, certainty is often temporary, and progress is made not by clinging to the past, but by embracing the unknown. As we continue to observe, model, and debate Pluto's place in the cosmos, we also gain a better understanding of our place in the universe. In this way, Pluto continues to inspire, a distant, icy body with a powerful impact on how we view our solar system, and a symbol of the ever-changing nature of science itself. Pluto has wide-ranging relevance for our understanding. Michio Kaku is yet another key figure in the conversation about Pluto. His work, along with that of Neil deGrasse Tyson, adds further insight into the dynamics and risks that could arise. His research builds on Tyson's, exploring how small shifts in Pluto's orbit could lead to a collision with Neptune or impact the stability of other celestial bodies. Koku's contributions help clarify how we might predict and possibly mitigate these risks as our understanding of distant solar system objects grows. To better comprehend the likelihood of a Pluto-Neptune collision, scientists rely on advanced simulations and models that track the gravitational forces between these two bodies over time. These models take into consideration the intricate interactions between Pluto and Neptune's orbits, as well as the influence of additional planets like Jupiter and Saturn. This research is essential not just for understanding Pluto's future, but also for refining our ability to predict the behavior of other objects in the solar system. Although Pluto and Neptune currently maintain a relatively stable relationship, uncertainty about the future of their orbits remains. The intricate gravitational dance that keeps the two planets on their present paths could change over vast periods of time. Even the smallest variation in their initial conditions could shift their orbits, potentially leading to a collision or another disruptive event. This unpredictability underscores the limitations of our current knowledge and the challenges ahead in studying the long-term dynamics of the solar system. Understanding the forces that affect Pluto's orbit is just one part of a much larger puzzle, and it provides valuable insight into the broader workings of our solar system. The interaction between Pluto and Neptune is an example of the delicate balance needed to preserve planetary orbits, not just for these two objects, but for the entire solar system. Studying Pluto's orbit is therefore vital for gaining a deeper understanding of the interactions between celestial bodies and how the solar system maintains equilibrium. As our investigation of space continues, studying Pluto and other far-off objects becomes increasingly important. These objects, though distant, hold valuable clues that could help us understand the origins and future of our solar system. Through investigating Pluto's unusual orbit and its potential interactions with Neptune, scientists are learning more about the forces shaping our cosmic neighborhood. These findings may have broader implications for the study of other distant objects, including exoplanets and stars in remote galaxies. Ongoing research into Pluto and Neptune also serves as a reminder of the need for continuing education in astrophysics. As Tyson and Koku have adapted their views in light of new findings, future scientists must remain adaptable and open to new ideas. The universe is constantly changing, and our understanding of it must evolve as well. As developments in technology advance, the more one investigates, the more surprising planetary orbits and the forces governing them will likely emerge. In conclusion, the possibility of a Pluto-Neptune collision remains an intriguing and complex topic that continues to captivate scientists and the public alike. The distinctive features of their orbits, coupled with the complex gravitational interactions, make this subject one of great interest. While the stability of Pluto's orbit is reassuring for now, the possibility of future changes serves as a reminder of space's unpredictable nature. As we continue to explore Pluto, Neptune, and other solar system objects, we gain deeper insights into the mechanics of our cosmic neighborhood. This not only enhances our understanding of the past and present but also shapes our predictions for the future, helping us better comprehend the vast and ever-evolving universe that we inhabit. The study of the relationship between Pluto and Neptune offers crucial insights into how the solar system works. Comprehending the dynamics of their orbits helps astronomers refine models of how distant objects interact within the vast expanse of space. Scientists who observe these interactions can not only forecast future events but also better understand the forces that govern the movement of planets, moons, and smaller objects across the cosmos. These advancements in space exploration are more than just about finding answers to specific questions, they are about developing broader theories that apply to a range of astronomical bodies. Research into Pluto and its orbit is an example of how focused studies on individual celestial objects can lead to significant findings regarding the universe as a whole. As our methods for observing space become more sophisticated, we may uncover even more complex behaviors in objects once thought too distant or too small to be of interest. In addition to the scientific curiosity surrounding Pluto and Neptune's orbits, the ongoing debate about Pluto's classification also highlights how our understanding of space is always evolving. As we gather more data and develop better technologies, what we know today may look completely different tomorrow. The journey toward comprehension of Pluto's role in the entire solar system is a flawless illustration of this constant growth in astronomical knowledge. The idea of a potential collision between Pluto and Neptune also underscores the dynamic and interconnected nature of the solar system. While such an event may seem distant or unlikely, the forces of gravity at play between planets demonstrate the complexity of their movements. Even the smallest force, such as a shift in the orbit of one planet, can set off a cascade of changes that ripple through the entire solar system. This interconnectedness is a reminder that space is not a static environment, but a constantly changing and evolving system that can catch us off guard at any turn. Moreover, the fact that a collision between Neptune and Pluto may be prevented by subtle forces of gravity over billions of years speaks to the precision and balance inherent in the solar system. While many might think of space as chaotic and unpredictable, these phenomena show that there is an underlying order and stability governing the motion of the planets. This knowledge has not only deepened our understanding of planetary orbits, but also demonstrated how these mechanisms have likely shaped the formation of our solar system and could continue to influence its future. As we venture deeper into the study of Pluto and Neptune, ongoing discoveries will undoubtedly push the limits of our comprehension. Scientists continue to refine their models and conduct simulations to predict how far-off objects will act, helping to uncover the deeper workings of the universe. Each new finding, no matter how small, contributes to a greater picture of the cosmic forces that govern our solar system and beyond. In essence, Pluto's potential for collision with Neptune, though remote, serves as a captivating reminder of the incredible complexity of our solar system. It is a testament to the ongoing quest for knowledge and a reflection of how scientific understanding constantly changes as new observations are made. While our grasp of these distant planets and their interactions may never be entirely complete, each discovery brings us closer to finding answers to space's mysteries, paving the way for future generations to explore the cosmos even more deeply. As we continue to expand our reach beyond Earth, missions to the outer solar system become not just a scientific endeavor but a necessity. The study of Pluto, Neptune, and their potential interactions is a cornerstone for understanding the larger mechanics that govern planetary systems, both in our galaxy and beyond. Each mission, whether it involves flybys, orbiters, or long-range telescopic observation, contributes layers of data that deepen our grasp of celestial motion. In particular, future missions focused on long-term orbital behavior will be critical. These efforts may involve deploying advanced probes equipped with highly sensitive instruments capable of measuring gravitational fluctuations, detecting minuscule orbital shifts, and mapping the intricate gravitational web that connects celestial bodies. With time and technology, we may be able to observe in real time how gravitational tugs between planets influence each other over decades or centuries. The importance of such research extends far beyond the academic. As humanity contemplates the future of space travel and even the colonization of other planets, understanding gravitational dynamics becomes essential for plotting safe interplanetary courses. A small miscalculation in a craft's trajectory could result in disaster if it fails to account for the evolving relationships between major celestial bodies like Pluto and Neptune. Furthermore, the lessons drawn from Pluto and Neptune serve as analogues for exoplanetary systems. The principles governing their orbits can help astronomers decode the movements and behaviors of distant planets orbiting other stars, some of which may reside in habitable zones. By refining our models here at home, we prepare ourselves to better interpret signals from other star systems and perhaps identify conditions that mirror those of Earth. These pursuits are not only scientific, they are profoundly philosophical. The more we learn about Pluto, Neptune, and their place in the cosmic clockwork, the more we are reminded of our own place in the universe. The dynamics between two cold, distant planets invite reflection on the fragility, precision, and elegance of the cosmos, a reminder that even the seemingly insignificant can wield vast influence when viewed on a cosmic scale. In the end, the study of Pluto and Neptune transcends data and equations. It is about curiosity, perseverance, and our unending desire to understand the universe that cradles us. And as we gaze into the night sky, pondering the invisible threads that hold the solar system together, we are reminded that discovery is a journey with no final destination, only ever deeper questions, and the promise of wonder in the search for answers.